So today's topic is yield of an open well. We know how to calculate the yield of a unlined well where water enters from the sides. Okay. But when it is a lined well, when this well is a lined well, this part periphery is made up of suppose concrete, then only water will be getting in from the bottom part. That is called lined open well. This was unlined open well. Okay. So in case of lined open well, hydraulics are behaving like very different compared to unlined open well. Okay. So in case of lined open well, we have discharge or Q is equal to area into velocity. Q is equal to area into velocity, where area is this area. There will be cavity formation and everything, but we just want to find out cross section area for the time being. It's equal to AV. Area is area of cross section of well. Velocity is velocity of flow of water. Okay. So primarily to find this yield of an open well, right now we are not considering unlined well. To find the discharge or yield of a lined open well, we have two methods. First method is constant water level method. Second method is recuperation method. Okay. So right now we are concentrating on first one. Constant water level method is very simple. First you will be, suppose this is the water level, initial water level. What initial water table. So you will be having water till here. So as first step, you will pump out water. You will get some water out so that there is a depression head. So that there is a variation of water table from this height to a particular height. We call it as small h till depression head. That is the first step. Okay. So suppose this h value will be prefixed. So it will be 20 centimeter or maybe 0.5 meter, 0.8 meter, etc. It can be any value depending on the soil strata and the well properties. Okay. So you will reduce this height into depression head, and then we start the real experiment or the real measurement. We will pump we will configure the pump so that depression head is unchanged. That's it. Okay. So we are fixed h, if suppose we are fixed h as 0.5 meter, arbitrarily say 0.5 meter, and suppose after initial pumping this initial water table has reached 0.5 meter, then we will reduce the pumping configuration, or we will reduce the pumping out quantity, and then we will vary this pumping out quantity so that this depression head stays at this level. Do you get it? If the water table rises, we will increase pumping so that it will lower. If water table lowers than this, we will decrease the pumping so that it retains in this level. So we will help in this well to attain a depression head, and we will configure or vary the discharge of the well so that there is constant depression head. Okay, it's as simple as that. Okay, so we have to work on this pump, whatever pump we are using for pumping out that varying quantity. We have to vary that pumping quantity time to time. Okay, so we will measure it. We will measure this pumping out quantity if suppose depression head is attained, and starting that from that time 2 hour or 3 hour duration of experiment is done, we vary this discharge and depression head is staying at the same height. Okay, so after this the pumped out water gives yield of well. Okay, it's very simple. So you get depression head to a particular height at H, and then ideally this depression head, this water table is unchanged. So whatever water that we have pumped out in varying quantities from that time onwards to 2 hour, 3 hour, 4 hour durations, whatever value we are measuring, whatever duration we are measuring, that quantity of water will be the yield. That is, that quantity of water will be coming directly from here, from the aquifer. It will be directly, quantity will be same because head is remaining as constant. So that's why constant water level method. Okay, so we will depress this level and we will keep it as constant. Then we will measure the pumped out water to get yield. Okay, so how much can you increase this value of H? H is depression head. There is a limit for increasing it. As H increases, yield also increases. As H increases, yield increases. If H is very high, yield will be more. If H is very low, like in here, yield will be less, obviously. Okay, so the value of H will determine yield. Okay, so also you cannot increase H beyond a certain value because there is a point called or a parameter called critical velocity. Critical velocity is the velocity through which water will be passing through the soil. Over that critical velocity, soil will be dislodged and coming out with water. Okay, suppose critical velocity of this particular soil is 0.8 meter per second, say 0.8 or 0.8 centimeter per second. Okay, up to 0.8 centimeter per second, whenever we pump out water, you will be getting pure water. If we reach 0.9 centimeter per second, 0.8 is critical velocity. If we reach a value or velocity more than critical velocity, soil particles in here will be dislodged or disturbed from this portion and will be getting pumped up with the water. Okay, so you will get muddy water. So you cannot increase H beyond a certain value. Okay, so I hope you get the concept. So there is a parameter called critical velocity. Beyond that velocity, soil particles will be dislodged from the strata, hence H cannot be considered. So in generally we adopt H as H is taken as 1/3 of critical head. Critical head is the corresponding height with respect to critical velocity. Suppose critical head is capital H. For capital H, there will be velocity of water will be critical velocity. So H will be equal to 1/3 of capital H. Okay. And also one more thing. Instead of taking area, while taking area for Q is equal to area into velocity, for taking area we will not be taking just the cross sectional area of well. We are supposed to take cross sectional area of well, but instead of it we will take cross sectional area of well into 4/3, because there will be a cavity formation. A portion of soil will be pumped up. So there will be a, if this is well, instead of this line you will be having a cavity like here. So you have to multiply with 1.33 or 4/3 with cross sectional area of well. Okay, so that are the 2 points you should be considering. And one more thing, if you are adopting critical head capital H for this constant water level method, you will get maximum yield. Maximum yield value. If you are taking small letter h, which is 1/3 of h, you will get safe yield or working yield. This small letter h is known as working head. Okay, so capital H is the critical head. If you are providing capital H on this constant water level method, you will get maximum yield as output V Q. Okay, if you are providing small letter h or working head, you will get safe yield as pumped out quantity. So I hope it's clear. That is constant water level method. So for constant water level method, we have an equation Q is equal to A into V, or you can write it as Q is equal to A into C into H, where A is cross sectional area of bottom of well, V is velocity of percolation of water through well, C is percolation intensity coefficient, or it can be expressed as K by H or K by L, that is permeability per head. The unit will be centimeter per second per unit head. Okay, unit head of each level of depression, and H is depression head. Okay, so you can prove the same equation with the help of Darcy's equation also. Q is equal to KIA, K into I can be written as H by L into A. Okay, and K by L into H into A. K by L is C. Okay, so same thing, A, C, H. Okay, so that was constant water level method. So second method to calculate yield of an open well, recuperation method. by the word recuperation. The meaning of recuperation is regaining of initial water table. As we know, if this is a lined open well, like this, and if this is the initial water table, or initial water level, we'll name it as AA. Okay, and we start pumping as usual. We start pumping out a certain quantity till it reaches another level, BB. Okay, then we stop pumping after the AA level of water level reaches BB by pumping a quantity. We stop pumping, and then what happens? Then recuperation happens. As the time progresses, this BB level, as the water is rising from this bottom, BB level will increase, and eventually it will rejoin the AA level. That process is called recuperation. Okay, so after a time t, capital at a time t, it will reach, say, this level, CC. Okay, and this height up to which we depressed it, we'll name it as H1, and the second height we'll name it as H2. H1 and H2. This was time 0. So 0 to capital T to reach CC. Okay, and suppose we are taking another small quantity at a very small time interval dt. At a very small time dt, you know where it is going. There is a level difference or decrease of h by dh. Okay, if suppose this is 1 second, there was a minute decrease of h by dh. Okay, so it is progressively going upwards to meet AA eventually. So we are taking a center point or arbitrary point, and suppose this height is termed as h. Okay, so this is the figure: h1, h2, h, dh, a, b, b, and cc at time t. Okay, so we have established basic idea. Now, considering this level difference or this volume increase, dV is the volume of water that got in through here, through the bottom of well, at a time dt, that is dV. dV is equal to, this is area A, area into dH. Pretty clear, right? This is the cross-sectional area. There will be an area, and through that area water is coming up. So area into dH, this small height, will give you volume of water that got in the well at the time dt. Okay, we'll name it as equation 1. Okay, and another way, dV you can write as q dt, discharge of well or discharge at this time into at small interval dt per 1 second. Okay, q dt, and q can be termed, q we know it is proportional to h. Why? If this depression head is increased, if it is up to this level, there will be immense water pressure coming up, so q will increase. if water level is only this much, there will be lesser pressure, so Q will decrease. So discharge Q is always proportional to depression head H. Okay, so we can assume that, or we can get to the equation as Q is equal to KH. Okay, so substituting this KH at Q, dV is equal to KH dt. We will term this equation as 2. Okay, both are RHS is dV, and so we can equate these LHS or RHS. Okay, so KH dt is equal to minus A dH. Why minus sign? Minus sign is because as dt is increasing, as the time is going on, as dt is increasing, what happens to H? H is decreasing. Initially it was H1, it is H2 after time t, it will be 0 after eventually. Okay, so as dt is increasing, H is decreasing, so there is minus sign. Okay, so obviously we have kept this dt and dh for integration, as we know. So integrating within the limits 0 to t, 0 when pumping was stopped at BB, when depression head was at H1, water level was at B. Capital T is depression head was at H2, level was at CC. Okay, for dt and H1 to H2 for dH. Okay, so H1 to H2 for H. Okay, so integrating K 0 to capital T dt is equal to A H1 to H2 dH by H. We are taking this H to this side. Okay, so there is a minus sign in here. So remove this, to remove this minus sign, we will exchange these limits. That is equal to A H2 to H1. So we will eliminate this minus sign, dH by H. Okay, so K by A is equal to, or K by A, what is integration of dt? T. So T minus 0 is equal to A, we have taken the as a denominator. So dH by H, 1 by H integration is log to the base E, H1 by H2. Clear? Log to the base E within the limits H2 to H1. So it is H1 to H1 by H2. Okay, so K by A is equal to 1 by T log to the base E, H1 by H2. This is the final equation, sort of final equation. So K by A is, the ratio K by A is termed as specific capacity or specific yield of this particle well. Okay, so K by A ratio is termed as specific capacity or specific yield of this particular well, that concerned particular well, and H1 and H2 we know by experiment, and T we will get it when it reaches from H1 to H2. Okay, so if you want to convert this log E into the base 10, it will be like 2.303 by T log to the base 10 H1 by H2. Okay, so I'll just say once again, we started the experiment when the initial water level was at AA. We pumped out a particular quantity till it reached BB, then we stopped pumping, then recuperation happens, and at capital T time it reached CC, and we are considering a minute time difference of dt. At that time there is a different head difference of dH with a volume difference of dV. So dV is equal to A into dH, equation 1, dV is equal to Q into dt, Q is equal to KH, we substitute, dV is equal to KH into dt, equation 2, equate these two, we have a minus sign here, integrating within the limit 0 to H and H1 to H2, 0 to T and H1 and H2, we will get the equation. Okay, so I hope it's clear, and it's not complete. So we have this equation, right? Keep that in mind. So I am just going to rub the rest. Okay, so we have K by A, and we know Q is equal to K into H. Okay, so how can we incorporate this value? Our final requirement is finding out yield or Q. Okay, so to find Q, we have to incorporate this section into this equation. So for that I am writing Q is equal to K by A into H. I am dividing and multiplying with cross section area, this area. Okay, so I have K by H in here, so I can substitute this in here. So Q is equal to 2.303 by T log to the base 10 H1 by H2 into A into H. So this is the final equation. Okay, so we just found a way to substitute K by A in this equation, that's it. Okay, so note that the unit of this equation will be based on T. If T is in hours, Q is in meter cube per hour. If T is in seconds, Q will be in cumex or meter cube per seconds, cumex. Okay, and if this value, this H is working head, we know what is critical head and working head. If H is working head, Q will be average safe field. If H is critical head, Q will be in maximum yield. Okay, so these two are just add-on informations. So the final equation is this: yield of open well by recuperation method. I hope you understood. It's pretty simple. Thank you.